Okay, in this video, we're going to cover section 1.4. Fair warning, this is kind of a long unit, so I'm probably going to have to split it into two videos, okay? So this is still unit 1, functions of graphs. First page is a lot of definitions. We have the definition of a function f, so this is our function f, from a set A to a set B can be visualized this way. So you have f, which is the function, and A maps to B. Or another way of thinking about that is that this is a relationship, here a relation, that assigns every element x, so every x value that's in the first set, to an element in B, which is y. Okay, we know this as the domain and the range, also known as the inputs and the outputs. Okay, so the set A is going to be our domain, set B is going to be the range. So a lot of stuff that you already know, just kind of in fancier language here. Okay, here's an example of a function that we are hopefully familiar with, some of us. We have the control buttons on a PlayStation, remote control, or Xbox. I'm not too familiar with Xbox, but PS4 all the way and all that. But let's say we have these directional buttons. Okay, we can say that the up button might be for, I don't know, the run mode. I'm sorry, the attack mode. So if you press up, that might mean attack for the avatar that you're using. Okay, to the left could be dodge. Okay, to the right could be run. Some pretty weird commands, but it is what it is. And then down could be jump. And if this was our example of a function, okay, we could say that set A, which is this part in pink, okay, is our domain, and our inputs would be the directional arrows. So up, left, right, and down, and that's what I have here listed. Set B would be our range, which would be the values that happen if you press this. So these directly depend on whatever you press. If you want your avatar to run, you're going to have to make sure you press the side key, the right button. Otherwise, he's not going to run, okay, or she's not going to run. So for set B, we have our range um, outputs as dodge, jump, run, and attack. Okay, so I'm going to go ahead and just list the ordered pairs now. When we are listing ordered pairs, we want to make sure that we do include the little curly brace, and then we're just going to put each one with its matching companion. So according to what I drew up here, the up button, I'm going to go ahead and I'll color code in the end. The up button goes with attack, so the up, attack, and that would be one ordered pair. The next ordered pair left goes with dodge. So left, dodge. Okay. The next one would be right, goes to run. So the right arrow is going to make you run. And the last one down goes to jump. Notice that all of these, and then curly brace, notice that all of these only point to one command, because if you had two different commands for one button, that would be very confusing. If you wanted your character in the game to, to jump, but if the down arrow means two different things, how are you going to know, which one, what he or she's going to do? If you want him to jump, but he ends up, running straight into a wall, well, that's going to affect your game stats, right? So this would be an example of a function that maybe we might be a little familiar with. Okay, all right, more definition stuff. So we have the characteristics of a function, and we have the same little drawing here that I did at the top. Function where A maps to B. So pretty much we have all these numbers in one set that map to something in another set, just like the example we had up here. Okay, first characteristic, each element x and A maps to an element y and b. So every x in here is going to have a value over here that it's going to map to. Okay, some of the elements in B may not be matched. So if you have, for instance, I'm going to go with a piecewise function or even a rational function, you might have some y values that, they're there, but there might be an asymptote there, or there might be a hole or something. on that x value, so therefore it's not going to actually be mapped to at all, and that's okay. Okay. Two or more elements x and a may be matched to the same element y and b. So you can have the y's repeating. That's what this means right here. A perfect example for this is a parabola. A parabola, and I really don't want to draw on this, but a parabola is that U-looking thing. And at some point, you're going to have a point on the left side that's going to be the same as the y side. So our y values will be the same, but you're going to have two different x's. Okay, and we'll see some examples where that might happen. And finally, an element x and a cannot be matched with two different y elements in b. That means x cannot be repeated, right? This is what most of us kind of associate with functions. You say, oh, well, the x can't repeat. And that is what this characteristic means here. Okay, so let's go ahead and go to the next page. This is a lot of definition stuff, guys, so hopefully it's review for you. I'm going to go through these examples fairly quickly. If you need to slow down, you can always pause the video or ask me questions later. Okay, so we have a few examples here that's asking if these are functions. So based on what we know about a function, we're going to answer yes or no, and I'm just going to explain why or why not. So example number 1 says the number of representatives x, so this is our domain part, right, our input from Texas, and the number of senators y from Texas. So because it's not giving us a specific value of x or y, it's just saying these guys and these guys, we can say that this is a function because one of the representatives might be matched to one of the guys in the Senate. Okay, so I'm going to go ahead and say yes for this one. Okay, there's an example of a verbal description. Example number 2. Okay, we have a table. So the tables, I think, are usually the easier ones to kind of notice because right away we can see here on my x's, okay, that we have two of the same x values. So that means that two elements x from our set A, whatever that A is, are the same. So right away I know that this is not going to work because if you were to plot this, so I'm just going to do a quick little graph here on the side to kind of show my point here. If you were to plot this, well, 2, let's say this is 2, and this is 10, and this is 11, okay? So we have 210, and we have 211. I'm talking about these two right here. So right away, this is going to fail the vertical line test, which we also know from Algebra 1 shows that a function is not a function if it fails this one. So if you have a picture or a relation that if you plot fails this test where you have two x's in the same vertical line, that means it's not a function. Okay, so this one would be a no. Okay, moving on. Example number 3, this is our graphical example. So far we've done verbal, tabular, and now this is going to be the graph one. We have ordered pairs, just kind of randomly in spots. It looks like this one kind of looks like a parabola, but remember that we can't base what the graph looks like on a few points, not all the time. So we're just going to look at the points we actually have. It looks like I can also use the vertical line test for this one. I could, if I don't want to do that, I could even label everything. I could say, well, this one looks like it's -2, 4. This one is -1, 0. This one is 0, -1, 1, 0, and 2, 4. So I could do it a couple ways. I could do it, if I do it this way, I can see that all of my x's, so all of my input values here are different. So we are good to go. Like one of the characteristics you saw on the page before, okay, you can see that the 4s do repeat here, which are the y values. But remember that y values can repeat. It's the x's that we want to be careful with. Okay, so this one's going to be a yes because none of our x's are repeated. They're the same. Okay, and it also passes the vertical line test. If I were to do my vertical line test here, you can see that it only passes through 1 point at each time that I test. Okay, so this should all be reviewed so far. The last one we're going to look at is algebraically. We might have, if you don't remember what the graph looks like, we might have to graph it. So let's go ahead and see how this works algebraically. For an equation like this, you want to solve for y and see if you can make this a function as related to x and y. So here's what I mean. You want to go ahead and put your line here, okay? And we're going to solve for y. So I'm going to go ahead and get this guy and move him over here. So to do that, I'm going to subtract both sides with x squared to get rid of that x squared. I think my pen is leaking here. So y is going to be equal to 1 minus x squared, or you could also do negative x squared plus 1. And if you remember your parabolas from algebra 2, okay, this is a quadratic function equation, I could say. It looks kind of like a U, okay, so it's going to be kind of like this. And there's some transformations on it. The negative here means I'm actually going to flip it. So this is actually going to be going down, okay? And that 1 means it's going to be shifted up by 1 unit. But if you don't know that, if you're not sure, what you can always do here is go ahead and just graph it, okay? And if you still haven't downloaded this app, guys, I highly recommend it, especially because we don't have access to our graphing calculators. Okay, remember this is the Wabbit Emu. You can try to get it out of the view there. But here it is. I don't know if hopefully you can see that. It might be a little bit dim. So I would just plug it in. So 1 minus x squared. Okay, and then I graph it, and I think it is a little bit hard to see. Maybe I can scoot it up. But there it is. There we go. That's better. So there's my graph. It does look like it's a function. If it was not a function, it would not have graphed. It would have said error or something like that. Okay, so this one is a function. We can go ahead and say yes. Okay, moving on. Get all those notes, lots of notes. All right, example 5. So here's another one that's going to be done algebraically. And this one, it's going to be a little bit different. Okay, so we're still going to solve it the same way. We're going to go ahead and move everything over. So in this case, it looks like I have to move this x right here. Okay, so plus x, that's going to get rid of this. Y squared is equal to 1 plus x. Okay, and then at this point, we have to take the square root of something. So square root, square root. Now, you need to be careful here because whenever you take the square root of something, mathematically, you are supposed to consider the positive and the negative of that square root. So I'm not actually going to say the square root of 1. I'm going to say the square root of the entire expression, but I do have to put this plus or minus. Okay, and if you try to graph this one, you're going to see that it's not going to work. You can't put a plus or minus. If you do two separate ones, y equals positive square root of 1 plus x and y equals negative square root of 1 plus x, it will kind of look like a oval circle. I'm not going to do it because I don't want to take too long with this, but you can try this one at home if you want. This one is not going to be a function. Okay, because we have the plus or minus, which is going to give us two functions, which is going to give us two functions, not one. In other words, you can't graph this, okay? All right. So again, I go ahead and you can try graphing this one on your own, okay? Maybe practice using that calculator if you still haven't downloaded it. All right, moving on. We have a note here, okay? Moving on to the next section, and this is actually function notation. I should have put that here at the top. Remember, this is going to be a very long unit, so we're trying to get through it. We can name or rename a function by f. This is how I do my f. Okay, if you want to use just f like that, that's fine too. Okay, so I like to do the cursive f. So we can use a function function f. Okay, this allows us to write our input output equation using function notation. That should be by, not b. So this is, again, a little bit more review. We have our input x, output f of x, and the equation f of x equals 1 minus x squared. So the one of the ones that we just used a few minutes ago, okay? For function notation, what we're going to do is we're going to use this to evaluate the function at given values of x. So here's a couple things you might want to remember, okay, or recall. F of x is read as the value of f at x, or the y value, or how I just said it, f of x. To find a value at this f of x, all we have to do is substitute the x value into the equation, okay? So here are some examples that I already worked out for you just to kind of refresh your memory. Let's say we had the same function, so f of x is equal to 1 minus x squared. For x is equal to -1, if I want to know what this value is at -1, I take that -1 and I plug it into here, okay, into anywhere that I have an x. You need to be careful because if there is an x square, remember for the x square, and I'll put a little note here, okay, for x square, when you're plugging stuff in, you want to think of it like this, parentheses square, okay? Because what happens, especially when there's negatives involved, is that people will forget that a negative square is actually positive. Okay, so you can see here in this example, -1 squared comes out, so this number right here came out to 1. And that's why when I did 1 minus this, I got 1 minus 1 is 0. Okay, next thing with 0, x equals 0, same deal. So we're going to take that 0 and plug it into the function where we had the x. So 1 minus 0 squared, 0 squared is just 0, 1 minus 0 is 1. Okay. By the way, guys, if you do catch a mistake, please let me know. There was a minor mistake in 1.3, so I don't want that to happen again. Okay, so let me know if you see something so I can fix it right away. Moving on. We're going to go ahead and do a few examples, but before we do that, I want to take a note that other variables can be used for x, usually in word problems, okay? So I believe a lot of the applications for quadratics, for instance, are physics problems actually, where you throw a basketball or a football. It's always some kind of sports ball, and it'll make kind of like a projectile motion. And those are usually denoted with a different symbol, such as t for the time related to the distance or height or whatever the idea is, but we can use different variables. That's the main point here. So here we have f of t, same deal where you had the x before, now you have a t. We can even rename this f of x or f of t into a brand new function and call it g. Okay, so just keep that in mind. And I'm sure you've seen this before. If you have more questions, just let me know. Here are some examples of how we're going to evaluate a function. Okay, we're going to let g of x equal to -x squared plus 4x minus 1, and we're going to find each value that's listed here. Okay, so this is, I'm going to use a different color because that green one's just not working for me right now. So this is our function. Okay, g of x is equal to all of that. And I'm going to find letter A, which is g of 3. So that means that instead of that x, I'm going to put a parentheses, okay, like so. And I'm going to plug in this 3 into every spot that I see a parentheses. Notice that I did keep that negative, so that negative is right here, okay? But my x is now represented by a parentheses, and that's where I mean as far as the be careful part, okay? So I'm going to go ahead and plug in my 3, and I kind of swapped colors here, okay? And we're going to evaluate the right side of this. So using our order of operations, okay, we do the parentheses first. So it looks like we don't really have anything inside the parentheses except for the number. So we're going to move on to the exponents. So 3 squared is 9. Bring down that negative. So we still have that negative here, okay, plus 4 times 3 minus 1, okay. Next, I'm going to go ahead and do the multiplication. So I have negative 9 plus 4 times 3 is 12. And I know my colors are all over the place. Sorry about that. Bring down the 1. Okay. So from here, we just add or subtract. Looks like we have negative 9 plus 12 is going to give us 3. 3 minus 1 is 2. Okay. So that means that my answer here is going to be g of 3 is equal to 2. Okay. And as a point, if I wanted to plot this point on the graph, I could say that the answer is going to be this 3. So 3, comma 2 as an ordered pair. Okay. So if you have any questions about that, let me know and I will, I can give you a different view of that if you need it. We're going to move on. We have another example for this same function. We have g of t now. So this one's a little bit easier because all I have to do for this one is, I'm going to just kind of do an arrow here, substitute everywhere I have an x. So I'm going to just redraw all this. So wherever I had those x's, I went ahead and just put a parentheses, okay? And I'm going to put that t in there now. So I'm going to take this t, whatever it stands for, and put it right here. And then just simplify. So if you're using a variable, typically you just want to, make it look a little bit nicer. So this one I can go ahead and just get rid of the parentheses because I'm going to leave it like that. 4 times t is just 4t minus 1. So g of t is just equal to all of this. So it kind of looks exactly like the original. I just literally swapped out the x for the t. Okay. All right. I think there's only one more for this little part right here. We have the last one, which is going to be a little bit lengthier. We have g of x plus 3. So now we have more than one term inside the parentheses. So pay close attention to this one. I'm going to start off the same way, and I'm going to put parentheses wherever I had those x's. I'm going to make them a little bit bigger because I see that I have to plug all this in. Okay, so negative parentheses squared, move this a little bit, plus 4 parentheses minus 1. Okay, same deal as the ones before. I'm just going to plug into these parentheses right here, that x plus 3. Okay, and I'm going to evaluate the right side of this. So here's where it gets a little tricky because we have this annoying little expression here that's going to make us do some work. Okay, so I'm going to expand this for you so you can see what this is supposed to look like. If we're squaring something like this, that means that there's two of them. Okay, like so. So this part right here that I'm boxing up lightly, this part right here represents this part. Okay, everything else I'm just going to bring it down. So plus 4 parentheses x plus 3, okay, minus 1. And I'm going to go ahead and work this part out first. So it looks like I'm going to have negative, and I'm going to put all this in parentheses. So I can't work with this negative until I deal with the FOIL here, okay? So let's put a big parentheses here. And if you forgot how to FOIL, remember I went over it very briefly in a different video, but it works like this. We have the first times the first, so we have x times x is going to be x squared, okay? Then the outside x times 3 is going to give me 3x. The inside, also 3x. And the last, so 3 times 3 is 9. Okay? Plus 4, and I'm just bringing this other stuff down. I'll deal with it in a little bit. If you want to be, get ahead of me, you're welcome to work this out if you want. Okay? Once we have this, we can go ahead and distribute this negative. Remember that the negative right here is the same as a negative 1. So we just have to multiply it in to everything here. And that's going to look like this. Negative 1 times x squared is negative x squared, or negative 1x squared. Okay. Negative 1 times 3x is minus 3x. Negative 1 times the other 3x is also minus 3x. Negative 1 times 9 is minus 9. Okay. Sorry if you hear my alarm. It keeps going off right now. So from there, we're going to go ahead and just bring down the rest again. So plus 4 times x plus 3 minus 1. Okay. And at this point, it's going to be a simple matter of distributing this part and then just combining like terms. So distribute here, and that's going to be, let's see, 4 times x is positive 4x. 4 times 3 is 12. Bring down the 1. We still have that minus 1. And then bring down all of this. So negative x squared minus 3x minus 3x minus 9. I know it's kind of a longer problem. Sorry. And then we just combine like terms. Okay. So at this point, it looks like the x squared is the only one of its kind. So negative x squared is solo. Okay. I like to keep track of my terms like that. Then we have negative 3x, and positive 4x. So it looks like we have negative 3 minus 3. That's going to be negative 6. And negative 6 plus 4 is negative 2x. So I can cross those out now. Okay. And then we finally have negative 9 plus 12 minus 1. Okay. So negative 9 plus 12 is going to give me 3. 3 minus 1 is 2. So it looks like g of x plus 3 is equal to all this. Negative x squared minus 2x plus 2. Okay. If you have any questions, again, as always, let me know and I will get to that. So let's double check one thing here. That's going to be negative 6 plus 2 plus 4. I'm sorry. Yeah, that looks good. Okay. All right, moving on. We're almost done with this video. I think I'm probably going to just do one more example. Yeah, one more example, then we'll do the rest in a separate video. So go ahead and write this down. We have a remark here concerning what we just saw in the previous example. Okay, it says that notice that our final answer, g of x plus 3, the last example, is not the same as the two before it. So you can't just say, oh, well, I don't want to do all that work. I'm just going to do this one. I'm going to add g of 3 because it's not going to give you the same thing. Once in a while, you might get lucky and get a problem that does work, but in general, this is not going to work. So it's this g of u plus v is not equal to g of u plus g of v. It's completely different. Okay. All right. Example number 7. Piecewise defined function. So we really should go more into this one. I'm hoping we see it later on because if you're going to be taking calculus, this is a good one to kind of look at. But for this example, I just want to focus on the function notation part. So let's really quickly define what a piecewise is. A piecewise function is a graph that looks like a bunch of pieces of a graph that just kind of got thrown on there and they don't really look that great. Okay, so this one looks like you have the first piece, which is the top part, x squared plus 1. So this is a parabola. It's some kind of quadratic. Okay, and this is only going to happen less than 0. So on our graph, okay, it's going to be like half a parabola, so to speak, on the left side wherever x is less than 0, so the negative numbers. Okay, the other piece of the graph is x minus 1, which is a line. So on the right side where x is positive or equal to 0, x is going to be a line. So just to kind of give you a little visual real quick, and then I'm just sketching this, so you're going to have to, bear with me here. It looks like x less than 0 is over here. Okay, so it's everything over here on this side. So an x greater than or equal to 0 is going to be everything right here. So on the first piece, This side, the parabola it goes up to here, then it kind of stops with an open circle because it's not equal to. On this side, we have this line. So it's x minus 1. That looks like it'll be about here somewhere. I don't know, something like that. Okay. So our graph will look something like that. It's going to look kind of weird. You don't really have to know too much about this part yet, but I just wanted to give you a visual on what we are talking about here. Okay. So this is what it is. We're going to evaluate these values given this function. So here's how it works. We're going to find f of -1 first. To evaluate a piecewise defined function at a given x value, we have to find where that x value falls. Okay, so in this case, -1 is our x. So x is equal to -1. Okay, so you want to say is -1 less than 0, or is it greater than or equal to 0? Okay, so in this case, x is less than 0 because -1 is less than 0. Okay, so if that's the case, we're going to use the first one. We're going to use x squared plus 1 for this one. And that's how these work. You have to find where this number lands, where does it land here, and then use the function that goes with it. So I'm going to go ahead and do that now. So we're going to have f of -1 equals parentheses squared plus 1, where this x value is -1. Okay, and then we just simplify it. So -1 squared, remember that anything squared is going to be positive, so that's going to be 1 plus the 1 that's here, which is 2. Okay, next one, letter B, f of 0. This one's a little tricky because you can see that both of them have a 0. So you have to decide, is it going to be less than 0, or is it greater than or equal to 0? Hopefully you chose the bottom one, okay? Because again, in this case, x is equal to 0, and the only one from these two that has an equal sign, sort of, is the second one, because it has that little line right here, okay? So we're going to use, let me put this in parentheses. So x, we're going to use this one, x is greater than or equal to 0. So use the second one, x minus 1, okay? I'm going to use a different color because I don't want to, it looks a little bit too much pink for me right now. So right here, I'm going to go ahead and use that one. So I have parentheses minus 1, and I'm going to go ahead and put that 0 in there. 0 minus 1 is just equal to -1. 2 more, f of 1. So we're going to do the same thing. I'm not going to write it this time. Hopefully you can follow me a little bit better. 1 is going to fall here because 1 is bigger than 0. So we're going to use this one again, x minus 1. Okay, so we're going to do parentheses minus 1. My x is just a 1. So 1 minus 1 is 0. Okay, and last but not least, -2. According to this, we have -2 is less than 0, so that would be the first equation. Okay, so parentheses squared plus 1, and inside the parentheses, we're going to put that -2 in there. Okay, -2 squared, -2 times -2 is 4. 4 plus 1 is 5. And then as a last thing, just that I want to show you, okay, so you can kind of see how this all ties together. If we were to make all these points, okay, this ordered pair would be -1, comma 2. This one would be 0, comma -1. This one would be 1, 0. And this one would be -2, 5. So if you wanted to, go above and beyond here, we could actually check these and see if it kind of falls into the little graph that I drew up here. Okay, so looking at the first one, -1, 2, -1, 2 would be about here. So this one looks good. 0, -1 is exactly this point that I put right here. So that one looks good too. 1, 0 is probably going to be this point right here, so we're good to go there. And last but not least, negative 2, 5 is probably going to be a little bit higher up on this parabola. So that means that our points make sense and our calculations are probably correct. Okay, so I'm going to go ahead and stop the video there because I think it's getting a little bit lengthy. I'll join you in for part 2 in a little bit. Thanks.